Hi, my name is Brant Robertson. I'm a professor of astronomy and astrophysics here at the University of California, Santa Cruz. I work on galaxy formation, so understanding the development and growth of galaxies over cosmic time. And I use James Webb Space Telescope, and specifically the NIRCam infrared camera on JWST, to look for distant galaxies and to try to understand where they come from, how they came to be, and how they evolve over time. I work with the NIRCam science team. This is the team that built and developed the infrared camera on JWST that looks from about 1 micron to 5 microns in the infrared. We use this camera to take deep pictures of the sky, very distant regions of the sky that we try to examine and to measure the properties of galaxies, especially galaxies in the very, very distant universe. As part of this, the team that I work with is called the JWST Advanced Deep Extragalactic Survey, or JADES. That is the largest program being executed with James Webb Space Telescope in the first year of observations. JWST is conducting many different, very exciting types of programs, especially for the extragalactic survey realm that you may be familiar with Hubble Space Telescope. Hubble Space Telescope took a variety of really intriguing images, the famous Hubble Ultra Deep Field that I helped acquire, the Candle survey, which was a large area near-infrared survey that was relatively shallow that my colleague Sandy Faber here at UC Santa Cruz conducted, and the Cosmos survey, which was the largest contiguous area that was observed with Hubble Space Telescope. Now with JWST, there are a large number of additional programs that will be executed. There is a Cosmos Webb survey, so this is a JWST version of the Cosmos survey that Hubble conducted, and this will survey relatively shallow with a relatively shallow depth, a very large area, about 0.6 square degrees on the sky, and that is the largest contiguous area that will be observed with JWST in the first couple of years of observations. There are also ultra-deep programs, so there's a survey called NG Deep, which will look very, very deeply over a portion of the sky called Good South. It will also observe parts of the Hubble Ultra Deep Field that HST originally observed. So they're really exciting areas of the sky, both large areas that are relatively shallow and also very narrow areas that JWST will be observing very deeply. James Webb Space Telescope is an amazing facility. It's a very large mirror, about 6.5 meters, hexagonally shaped, so that it could fold up to fit in the rocket that ESA launched on December 25th of last year. The mirrors on JWST are coated with gold, so that they're very reflective in the infrared, and this makes it an excellent facility for looking at infrared light. The telescope itself is protected by a giant sun shield, which is about the size of a tennis court. And this sun shield allows for JWST to be very cold on one side of the telescope, which allows us to have the instruments to be very cold and therefore very sensitive in the infrared. They're not glowing in infrared light. And this allows you to see very faint objects in the infrared that you otherwise would not be able to see. JWST has a variety of instruments. So there's the NIRCam instrument that I work with, which is the near infrared camera that looks from 1 to 5 microns. There's also the mid-infrared camera called MIRI, the mid-infrared instrument, MIRI. MIRI looks at beyond 5 microns, so it's looking at colder gas and dust and stars in the universe. There's also the NIRSpec, the near-infrared spectrograph, which takes infrared light and disperses it so that you can see each individual wavelength of light one by one, and that allows you to look at detailed features in the light of galaxies and stars in the distant universe. And there's also a near-infrared slitless spectrograph called NIRIS, which allows you to take an image of the sky, but color by color, so you actually spread out the light wavelength by wavelength over the whole image. And this also allows you to see the fine details of light emitted by galaxies and stars. As we acquire data with JWST, this data comes down in a format that needs some processing. So we need to be able to calibrate the data. So the numbers in the images that we actually see, we have to know how that translates into a brightness of the object. So we need to know how to translate the numbers into physical units. So that's the calibration procedure. Each of the individual images that you take with JWST cover a relatively small area of the sky. So if you want to make a large image, you have to mosaic individual pointings of the telescope. And that means that you have to register these images very carefully on the sky. You have to know exactly where they're located. So that mosaicing process also involves a fairly detailed set of steps that we conduct. Then once we make an image of the sky in mosaic, like what you see on my screen, we want to be able to find the objects in the image. So we have to produce algorithms that go through and identify the stars and the galaxies in the image, and then make measurements object by object. How bright is each individual object? And that's yet another part of the analysis pipeline. So each step along the way, people have been working, our team has been working to try to develop as best as we can techniques to accurately and precisely measure the individual object properties, to mosaic on the sky correctly, and to calibrate the data precisely. In the infrared, of course, we don't see with our own eyes in the infrared. So the colors of the objects are, we say false colors. So we assign, when we make a multicolor object like this, the red, blue, and green colors that you see in the image, those are assigned to specific wavelengths that JWST observes with. So we might say that the bluest color that JWST observes with is about 0.9 microns, or around a micron. This is actually further in the red than we can see with our own eyes, but when we use an RGB image of the sky, we're actually just assigning blue to be a color that is further in the red than we can even see. We might then assign, say, 1.5 microns to green, and to red, maybe even 4 microns, to give you a dynamic red, blue, green color image that actually corresponds to wavelengths that JWST can see. The calibration procedure still right now is somewhat manual. We get a set of data from the pipelines that have been developed for JWST, but the facility has not been fully calibrated yet. So each individual set of data, people are still very much in the details trying to make sure that the data is well calibrated. So that process is still ongoing. We hope that there will be some more definite set of calibrations soon enough, but this is something that people are still very much looking at. JWST lies about 1.5 million kilometers away from Earth. It's very far away. So we can't actually go to the telescope to fix it. However, there are onboard various types of maintenance that can be produced. So for instance, you may have heard that JWST has been hit by micrometeoroids, so small pieces of space dust and other debris that have hit the mirror. And some of these have actually moved the mirrors slightly. That, if we could not change the alignment of the mirrors, would defocus the telescope. So what we do then is, after these events occur, the telescope is actually fixed. It's the mirror segments are rotated and moved in and out in focus, so that the whole facility actually can refocus itself. And that's the level of maintenance that we're able to do with JWST. There's also a variety of procedures that can unload momentum of the telescope that builds up over time. There are also a set of thrusters on the facility to keep it in its orbit. And those kinds of low-level maintenance operations are happening all of the time with the facility. When JWST sends down data to us here at Earth, that information is stored in a set of databases which are run by the Space Telescope Institute in Baltimore, Maryland, in a facility called MAST. And astronomers all over the world, when they want to access that data, they log on to MAST and they download all of the data that their observing program has acquired. So All of the data collected by JWST is available through MAST. Not all of it is yet public, but it will be made public over time. Some data is public, and people out at home can download the data themselves and look at it, just like professional astronomers do throughout the world. So our collaboration, when we download our data, we of course process it on computers, and we store it. Actually, some of the data is stored here locally here at UC Santa Cruz, and then we provide it, again, these reduced data products to our collaborators throughout the world. The first results with JWST have been amazing, absolutely fantastic. The facility works better than we could have dreamed. The sharpness of the images is well beyond our expectations, and the lifetime that's expected for JWST is much longer than we were originally hoping. So there's really going to be a huge rewriting of cosmic history with JWST. On the new results with JWST, I'm extremely interested in them. Of course, we've produced some ourselves, which we think are amazing. Of course, over time will tell. We will actually go in and see whether or not all of these results are reliable. We hope that they are. Over time, more and more data will be acquired. And so we'll learn more and more over time about the distant universe, about these very distant massive galaxies that appear to be, how many very large bright galaxies there are in the distant universe. These are things that JWST is saying, some very interesting early information about, but it needs validation, it needs verification, and so more data will really tell the story. The first year of observations with JWST, we're really getting our feet wet. We're executing programs. We're looking in a window of wavelength and of sensitivity that we've never seen before with telescopes as astronomers. So there's really a lot of exciting and new information. But I think it will take us a couple of years, probably a couple of cycles, we call them. A cycle is when we propose for observations and then they're executed sequentially. It will take us a couple of cycles with JWST to really be able to answer some of the mysterious questions the early data has provided to us. JWST has a unique capability of looking far back into the distant universe. And one of the most interesting topics that JWST can address is this process of cosmic reionization. This is the epoch in the early universe, in the first billion years of cosmic time, where most of the gas in the universe went from completely neutral to completely ionized as we see it today. And we think that that cosmic reionization process was produced by galaxies, but we're not exactly sure which galaxies actually triggered cosmic reionization. We don't know if it was the bright ones, we don't know if it was the faint ones, we don't know if it was some special type of galaxy. But JWST, because it's so sensitive and the infrared light that it detects is really able to look for these very distant galaxies, we hope that JWST can finally settle which galaxies reionize the universe.